Well, we're here, right? So, last talk of the school, but after, there might be some posters, presentations, and coffee break. But here we are. So it's my pleasure to introduce Mykola Khrypchenko from Universidade Federal de Santa Catarina here in our campus, who talk to us about cross modules over inverse semigroups and their cohomological interpretation.
Mm. Thank you. Thank you, Daniel. Thanks for the invitation. Thank you for the organizer. It's really, uh, I imagine how difficult it was to organize a school. I mean, in in a presential mode. And I apologize for giving the same talk that I gave at the seminar of operator algebras last year. So this is a joint work with Mikhailo Dokuchaev and Mayumi Makuta from the University of São Paulo. The original idea behind this work was trying to find another interpretation of the third cohomology group, the third partial cohomology group of a group in the context of cross modules. Then when we started to look what's going on, for example, in the case of inverse semigroups, we find out that there are no works even in the case of inverse semigroup about that. And we know that there is a relation between partial group cohomology and the cohomology of inverse semigroups. So we started this work in the context of inverse semigroups. We thought that it would be a first part, and then we would pass to the case of partial actions. But we soon realized that even in the case of inverse semigroups, it gets a lot of work to do, and it cannot fit in one article. So that's why this result appears, and it was planned as a preliminary result, but it finally turned out to be a main result of this work. Well, let me first recall what's going on in the classical case of groups. So what is a cross module over a group? It's an action of a group G on another group N, which is not necessarily abelian, together with a homomorphism which acts from the group N to G, which relates this action of G with conjugacy actions. So the image of N acts on N prime by conjugation. And if you act on N by G, then apply B, it's the same as apply B and conjugate in this group G. So this pair consisting of an action and the homomorphism B is called a cross G module. Of course, there exist other definitions of a cross module. As Guillermo told me today, there exists a definition in a pure categorical context. But I will give this classical definition. It appeared in the work of Whitehead in the 40s, and then it was used again by Maclane in 50s, I guess. So, well, some examples are the following. Of course, you can take N to be abelian and beta to be trivial map. Then it gives you usual G module. So that means usual G actions on abelian groups. You can also obtain normal subgroups of G as particular cases. In this case, you take the inclusion map and the action of G by N by conjugation. And you can also take G to be the whole automorphism group and beta of N to be the conjugation by the element N in this group. So these are three examples. Well, first of all, what can you obtain directly from the definition is that the image of N under beta is a normal subgroup of G, so that you can form this four-term exact sequence. You take the kernel of beta, you take the co-kernel of beta here, and so you have this four-term exact sequence. This is an epimorphism, and this is a monomorphism. Now, what's more can you get from the definition is that the group A is central in N, the group A, which is the kernel of beta, which is inside N. it is central there. And if you can observe that the elements of G, they leave A invariant. So, and moreover, the image of N under beta, it acts trivially on the elements of A. So that you have the quotient H, which acts in the usual sense on A, and A is abelian group, so you have a usual H module over A. So starting from a cross module, G cross module of A over A, you have a usual H module over A, and you have that four-term exact sequence. Now, you can define equivalence of such four-term exact sequences in a usual sense. In usual way, you take two sequences, you put them horizontally, then you have identity maps on the first and the fourth terms, and you have two vertical homomorphisms which make this 3-square commute. And okay, this is not an equivalence relation, but you can generate equivalence relation by this relation, and that gives you equivalence of exact sequences. And it was proved by Maclane, I guess, that there's a one-to-one correspondence between such equivalence classes and the elements of the third cohomology group of that group H with values in the module A. Now, let me give you some idea of the proof. In one direction, it is more or less standard way. If you have an exact sequence, you take an transversal of this epimorphism, then you multiply the images under this transversal, you observe that it is the image of the product up to some factor which acts like if it were a 3-term exact sequence, it would be a 2-cos cycle. But now it's not a 2-cos cycle. If you apply the boundary operator, then it gives you something which depends on 3 variables, and it is in fact a 3-cos cycle. And you show that this 3-cos cycle is up to boundary, it's invariant under the choice of the transversal. So this gives you a well-defined element of the third cohomology group. So this way is standard. And the other direction is quite, for me, at least to my opinion, it's non-clear and non-trivial. So what you get? You have an H module A, and you have a 3-cos cycle. First of all, you need to construct those two intermediate terms in your 4-term exact sequence. That group G and group N, and of course beta between them. So G would be the free group over H seen as an alphabet. So this huge free group, and you have natural epimorphism from G to H, which sends a letter to the element of H seen as which sends the letter to itself seen as an element of H. Yes, and this map has kernel. Okay, it's a subgroup. It's a normal subgroup of the free group. Any subgroup of a free group is free. In fact, you can prove that it's freely generated by such words. You can use some technique you can find it, I think, in Kargapolov-Merzdakov book on group theory, that it's freely generated. How to find free generators of a subgroup of a free group. So, and you have your G, yes, you have your kernel R. Now you define N to be the direct product of A, this A, yes, and this R kernel. So you have N, yes, you have G. How do you define the structure of your cross module? So you should define the annexion of G over N. So you may define it, of course, since G is a free group, you can define it only on generators, you can define the action of a letter. And since this itself is a product of A and again a free group, it's enough to define it again on this first component. Yes, this letter acts just using the action of H on A. And on the second component, it's quite it's why it seems to be well complicated. Well, it involves the cocycle C, which is given. It puts it on the first coordinate, and on the second coordinate you have this product. Well, it's written this way to show that it's an element of the free group H. But if you rewrite it, yes, using this definition, it's nothing less than nothing more than just the conjugation of this word by this letter in the free group. So this is the action. Yes, on the first coordinate you just use the action of H, and on the second coordinate you conjugate, and there this tricocycle appears here. Yes, you have already seen a definition of a tricocycle on this on this school. So, but nevertheless, I will give it in the semigroup inverse semigroup case, and it's almost the same. So this gives you an action, and you have your beta, which just sends. Okay, an element of n is a pair. You just send it to the second coordinate, and so it gives you an element of G. Again, the second coordinate is an element of this kernel, and the kernel is a subgroup of the free group, so it sits inside the group G, and it's a homomorphism, of course. Now you prove that cohomologous cocycles induce equivalent extensions and equivalent sequences. So you have this map in the opposite direction, and you have a one-to-one correspondence between three cocycles, three cohomologies, and four-term exact sequences this way. Now, before giving the definition of cross module over inverse semigroup, let me first recall what is a module, a usual sense over an inverse semigroup, because it's not that, maybe it looks not that trivial, maybe. It's not like a module over a semigroup where you just take an action of a semigroup over an abelian group. No. No, a module over an inverse semigroup S is a commutative inverse semigroup, or in other words, it's a semi-lattice of abelian groups. With an action of S on A, of course, it should be an action, but it should also satisfy the following. You should have an isomorphism between idempotents. So you cannot take an arbitrary inverse semigroup here. It should have the same, well, isomorphic semi-lattice of idempotents. And this isomorphism should satisfy the following. This action. If you act on A by an idempotent, this is just a multiplication on the left. Well, by the same idempotent up to this isomorphism alpha. And if you act by S on an idempotent, then it's a conjugation. You know that any inverse semigroup acts on its idempotents by conjugation. And again, you apply this alpha to stay inside your A. So these two conditions should be satisfied. And of course, it should be an action. It should act by endomorphisms in the usual sense, like a semigroup acts. Now, if you have an S module, how do you define cohomology? Of course, there is a universal way to define cohomologies. You may show that S modules, they form an abelian category, and that has enough projectives. In fact, it has free modules. You may show that you may define a trivial module. You may construct projective resolution. You can apply the functor hom up to this projective resolution. This gives you a cochain complex of abelian groups, and taking the cohomologies of this complex, it gives you cohomology. And of course, it's a general fact that this does not depend on the choice of the resolution. And in the article where this was defined, the author, Hans Lausch, he gave several resolutions which serve to obtain explicit formulas for cohomology groups of your S. Well, but one of these resolutions, which reminds a lot this classical bar resolution from the group cohomology, it uses the fact that S is served only for monoids. If S is a monoid, of course, A should also be monoid in this case, because they have the same idempotence, isomorphic idempotence. So I use this well, if your semigroup does not have identity element, if it's not a monoid, you can adjoin a monoid identity and consider this S1 and A1, the semigroups. And now you have identity elements, and now you can use that resolution that gives you that formulas, nice formulas, which remind you the formulas from the group cohomology. Well, so I will use this. I will not recall that that resolution to just give you the exact formulas, the explicit formulas. So n cochains will be the maps of n elements from S to A, but which take their values in the appropriate group component of A. So this means those elements of A such that element times its inverse is this idempotent. So this is the group inside A. Under coordinate-wise multiplication, such functions, they form an abelian group. So you have abelian groups of n cochains. Now when you define boundary operator, it has exactly the same form as you may have seen in the group case. The difference is that I use here the multiplicative notation. So instead of sum, I write product, and instead of minus the coefficient -1 to the I use this exponent. And the rest is the same, has the same form. So that's how you have a cochain complex of abelian groups. Now this isn't just a usual way to define cohomology groups. You have the kernels of those coboundary maps, which are cocycles. You have images, which are coboundaries, and you have quotients, which are cohomologies. So I use the same terminology from the group case. Well, okay. Now we define this cohomology of S1 with values in A1. Maybe it's different from the cohomology of S with values in A, which is defined in a very theoretical way. Now, and in fact, it may be different in dimension 0 and 1, but starting from 2, they are isomorphic. So you can adjoin 1 and here, and to use that nice resolution, nice formulas, and this gives you cohomology, the same cohomology. And since I will be working with the third group, so I may use this fact, and everything works. Now, in fact, I will need a more specific cohomology group. You may define, since you have an inverse semigroup, you have a natural partial order on that semigroup, you may define what is called a order-preserving cochain. So this is a function which preserves order. If you have n elements of your S, another n tuple, such that they are ordered, so that the images will be ordered as well in this semigroup A. So this is what I call order preserving. They form a subgroup of these cochains, which I denote this way. In fact, coboundary operator, it respects this subgroup. So you have a cochain of abelian groups. Again, this is a standard way to define cohomologies from this cochain complex. So I will call them order preserving cohomologies. And these cohomologies, in fact, they appeared in our earlier work where we related this cohomology with partial group cohomology. But I will not talk about this today. And it has become it has appeared again in this work in a natural way. Well, now if you have usual modules, if you have cohomology, let's talk about cross modules. If you already have definition of a usual module, yes, one more ingredient that I will be needing is the following. In a usual module over an inverse semigroup, that elements of S, they acted as endomorphisms over A. Now, if you want to extend it to the non-commutative case, you will need to something more, which has more properties, some stronger notion of an endomorphism. It's called a relatively invertible. It means the following, that there exists some a kind of inverse. Well, it's inverse up to, it's like partially inverse, because if you compose them, it gives you a multiplication on the sum by some idempotence, and in the opposite direction as well. And moreover, this acts as identity on the image, and this acts as identity of this phi of A. So it's a relatively invertible, and in fact, relatively invertible, they form an inverse semigroup. Well, usual endomorphisms of A, they form just a semigroup, not inverse. But I will need an inverse semigroup, and these are relatively invertible semigroup, relatively invertible endomorphisms. In fact, it's in this inverse semigroup is isomorphic to the semigroup of isomorphisms between principal ideals of A. Maybe this is more easy way to look at this semigroup. And now, but what about the definition of a cross module? You just take, okay, inverse semigroup, you have a semilattice of groups, not necessarily abelian, of course. You have an action. You want this action to be similar to the action which appeared in the definition of a usual module, and these are these two conditions, which exactly the same as in the case of a usual module. But now you want that map in the opposite direction. Here it should be okay. Of course, it should be a semigroup homomorphism, but you also require that it be idempotent separating, which means that it's injective on the idempotence. And moreover, on the idempotence, it's in fact the inverse of alpha. You know that alpha is that isomorphism between idempotence, which you also require here. Now, these two conditions, they repeat the same conditions in the group case. So you have two conditions from the definition of a module over an inverse semigroup, and you have two conditions from the definition of a cross module over a group. And you combine them, and you have a definition of a crossless module. What we have from this definition, we may define A as, you remember that A was the kernel of beta. Now the kernel means the pre-image of idempotence. In the group case, it's pre-image of 1, and in this case, it's pre-image of idempotence of S. And again, it's a semilattice of abelian groups, which is contained in the center. Well, so it's okay. We may define some action on this A little bit later. Now, what about the co-kernel? Can we construct it? Yes. If you take the image of this N, and you take its group components and the images by beta, you have a group kernel normal system. Again, it's a you know that in a group case, you may define a quotient of your group by a normal subgroup. In the semigroup case, in the inverse semigroup case, you may define the quotient of your inverse semigroup by some collection of classes of idempotence, such that if each one contains exactly one idempotent, it's a group. And this is called group kernel normal system. You may define the quotient, you may define the congruence, and the quotient semigroup, and it will be inverse. So this is that co-kernel. You have the natural apomorphism pi, and it is idempotent separating because it's group kernel normal system. And again, this is somehow some kind of a exactness of your sequence which you obtain. So you obtain this sequence of inverse semigroups. Yes, this I, which was the kernel of beta, with this T, which was the co-kernel, again, in the semigroup sense. And you call it a cross-module extension if this N is a cross-module, beta is the corresponding homomorphism, I is monomorphism, pi is an idempotent separating apomorphism, and this says you that this sequence is exact in this term, and this says that it's exact in this term. Well, the definition of equivalence is the same. You have to two sequences, you have two vertical homomorphisms, which make this picture commute. All these three squares should commute. And moreover, it should respect the action, or you have your action, you have your cross module here, you have cross module here, you have the corresponding actions, and so your phi1 and phi2 should respect these actions. Well, now you may show that any cross-module extension of A by T, it induces a T-module structure on A in the sense of a module of an inverse semigroup. And equivalent extensions, they give you the same module structure. Now, so that I can fix this module here, and I say that a cross-module extension of a T module of A by T is a cross-module in which this T module structure, this induced T module structure, is the given. Now, I denote by ETA those extensions which give you the equivalence classes of such extensions with TA fixed and with the module structure fixed as well of T on A. Well, now the easy part is the following. If you have an extension, how do you define the cocycle? Well, it almost repeats the group case with some modifications. But before that, you should define you should talk about a little bit about transversals, since you will be using them in your definition. Now, you know, if you have a homomorphism between inverse semigroups, you may define, okay, a transversal is a map which acts in the opposite direction, and such that it is essentially the choice of pre-images. Now, you may require that it respects idempotence. Okay, you may choose a transversal which respects idempotence. Always, if you have a homomorphism between inverse semigroups, and I'll say that. So this is just a notation. Right? Yes. Phi of S to T. Yes, you're right. Yes, from phi of S to T. Thank you. And yeah, I'll consider the more general case where rho is not epimorphism, it's not surjective. So yeah, it should be phi of S. And you can always choose a transversal which respects idempotence if you have a homomorphism between inverse semigroups. Well, and now the construction is the following. You have your pi here, you choose a transversal of this pi. As I said, you multiply these two guys. You have this up to, and this factor appears here. It lives in this group component. Then you lift it to a map which takes values here in an arbitrary way. And then if you calculate its coboundary of this map, it appears to be almost cocycle with up to this term that appears. And this one will be, in fact, a 3-cochain. In fact, to be a 3-cocycle. And again, if you choose another transversal, if you lift your map small f in a different way, it will give you a cohomologous cocycle. So you have, and even more, if you have equivalent extensions, it gives you cohomologous cocycle. So you have this map from equivalence classes of extensions to the third cohomology group. And you show that this is this cohomology group as I defined above. Now I will need some specific extensions which produce these order-preserving cohomology groups. And these are the following. Okay, you can always choose a transversal of your homomorphism, but it's not clear whether you can choose a transversal which preserves order as well as a map. And I said that rho is order-preserving if it satisfies this condition. Well, what are order-preserving transversals? If it's order-preserving in respects idempotence at the same time, then it's almost a splitting, almost a homomorphism. It splits like this, products in which one element is an idempotent, but not all the products. Now I call an extension admissible if those two maps in my exact sequence, they possess order preserving transversals, which as well respect idempotence. And I will denote the equivalence classes of such extensions this way. Okay, you may show that any equivalent extension will also be admissible. So you have this set, and it's easy to see that admissible extensions, they produce order preserving cocycles and order preserving cohomologies. Okay, well, so you have a map in this direction. It was relatively easy. Now what's going on in the opposite direction? This is the main part. First of all, if you have a module, you need those two intermediate inverse semigroups. What is the candidate of that semigroup? Okay, in the group case, you had the free group. But if you, well, okay, you may say, let me take the free inverse semigroup. Well, you may take in free inverse semigroups. Well, the problem is that it has a lot of idempotence, much more than the original semigroup S. And you want that all the semigroups in your sequences had isomorphic idempotence. So this would not work. But what works, eventually worked, was a unitary cover. So there is a way to, given an inverse semigroup, there is a way to construct, in fact, several ways to construct a unitary inverse semigroup, which maps onto your given inverse semigroup. The corresponding epimorphism is idempotent separating, and moreover, you would like, if you fix the group G, you may talk about the unitary covers through G. So if G is fixed, those are unitary covers which have the maximum group image isomorphic to the group G. And it turned out that it's very useful in our case. We found it in this article where the authors constructed a unitary cover through a free group. And this was in fact was that ingredient which worked in our case. Okay, they proved that each inverse semigroup admits unitary covers. They gave several ways to construct them, and that one which we used is the free cover, the unitary cover through a free group. And the construction is as follows. Okay, you have inverse semigroup T. Consider the alphabet. Okay, consider its elements as letters, yes, but you also take the formal inverses of that letters. And you consider the free semigroup, usual free semigroup, not inverse, over this alphabet. Of course, you have this epimorphism, which sends the letter to the corresponding element of the group, of the inverse semigroup. And you also have another epimorphism, which sends this letter to the letter in the free group over the alphabet T. So this is the free group. And it works this way. So you have two epimorphisms to your T and to the free group over T. And this way you define phi capital as follows. So it gives you the following. Given an element of T, you consider all the representation of this element in all the words in the free semigroup whose products, which represent your element, such that the product of letters gives you your element. Now, and you, again, to any of such words, you apply psi. You map it, so you send it to the free group, which means the following. In your word, you could have subwords of the form T inverse. And you could not cancel them in the free semigroup, but in the free group you can. So you just cancel, if you just make this cancellation, it gives you an element of the free group. So this sends T to all the words in the free group which represent this T. Now they defined the cover in the following way. The cover was the set of pairs, element of T, and a word in the free group, such that it represents this element of T in this sense. If you multiply its letters, it gives you, well, not exactly. If you find an element which represents and then make the cancellation, that it gives you this element of the free group. Well, it looks somehow strange, maybe complicated to at least to me. It was looking that way. So we found some equivalent way to represent the elements of this semigroup, this cover. Okay, let me call a word irreducible if it has no subwords of this form. A word in the free semigroup. And this inverse means the inverse, you know, you have letters, you have inverses of letters. So this means word and its inverse in a formal sense. Now, you know that any word in your free group admits a unique representation as a non-empty irreducible word. So I will denote this way. So with any word in the free group, I associate a word in the free semigroup, which is irreducible in this sense. So you have a map this from the free group without the identity element to the free inverse, to the free semigroup, not inverse. Now, given this, you may define nu of W applying phi. So you make cancellations in your word W here, and then you multiply the letters. And this gives you an element of T, but I will need also the image of the identity, which is an empty word. And I will send it to 1, which is adjoined here. And I join 1 to my T. Now we may show that the elements of this unitary cover, they are those pairs, TW, yes, but the condition is different here. The condition, which is equivalent, but looks different, is the following. T is less than or equal to nu of W. Less than or equal to in the with respect to the natural partial order in T. So this is the condition, which in my opinion, looks, at least to me, it looks easier to work with. You may show that the idempotents of this semigroup S, they are exactly this way. There's exactly these pairs where E, the second component, is an empty word. So it's in a one-to-one correspondence with the idempotence of T, which is what we wanted, in fact. And you may observe also that if you take T to be a group, okay, T is an inverse semigroup, but it may be a group. Okay, if it's a group, then on a group, this natural partial order is just equality. So in a group, you have, instead of this pair, you have just one word, W. Okay, this first component is uniquely determined by the second one. So you have one-to-one correspondence between the elements of this, between these pairs and the words in a free group. So you have a free group over T, which is again a good signal, because you know that in the group case, this group G that you constructed, it was free group over your initial group, original group. And you see that this construction restricts to this group construction in the group theory. It gives you the free group. And if you had taken free inverse semigroup, it would not, certainly would not restrict to a free group, because free inverse semigroup over a group is not a group. It's an inverse semigroup. Well, now, so we have that S. What about another inverse, the second term in our sequence? It will be the following. Okay, in the group case, you had direct product. You had kernel and multiplied by A. Okay, in this case, you have the kernel of, I denote it by K. it turns out to be a semilattice of groups, abelian groups. No, just groups. Sorry, which have this way, this form. Now, okay, you could multiply directly one semigroup by another one. It would give you an inverse semigroup, but the problem is, again, idempotency. It would give you an inverse semigroup which has much more idempotency than the original ones, because the idempotency would be pairs of idempotency, like square of idempotency. So it would not serve. But what serves is you could take each group component of A and each group component of K, the corresponding two components, multiply them directly. This is a group. And then join them formally over all the idempotents. And you define the structure of semigroup in a natural way on this union, on this formal union. And this gives you a semilattice of groups, of course, by the definition. And this is, I think this is the direct product of two semilattices of groups in a category with fixed indexing semilattice. You may define this category. You may, I think that it is a direct product in this category. Okay, this gives you n, and the elements of n. Okay, these elements are elements of A, and these are pairs. Yes, so you may join them in triples this way. A is from the group component of A, and this is word from the free group. This is idempotent, such that the idempotent is less than this reduced word multiplied in T. Yeah, so this is n. Now, again, the difficult part is to define your action of the group S over n. So the group S, whose elements are pairs, the group n, whose elements are triples, you should define an action of a pair over a triple. Well, what is, again, what is easy to do is to define this, okay, this embedding of A into n. It's easy to do. It's easy to construct this isomorphism. It's easy to construct beta. And what about lambda? This is what really needs a cocycle C. And I take order preserving cocycle. For non-order preserving cocycle, I cannot imagine what to do. Yeah. Now, the proposition says that there exists a homomorphism which defines a cross-module structure of n. I just can show you some formulas maybe how to construct it. Yes, so you have this pair S, you have this triple. How does this pair act on a triple? So on the second component, it acts by conjugation. On the third component, it acts by conjugation in the free semigroup. But on the first component, how does it act? You have an action of T on A is coming from the module structure, and you have this factor here, which involves cocycle, which is defined in terms of cocycle. And this is the most complicated part. Well, how does it work? Okay, you should define first psi of T, which will be defined on the next slide, and applied it to irreducible word if it's non-empty. Now, what about psi? Well, it will act in the following way. First of all, if your W begins with a letter, with an inverse of a letter, you would like to transform it to a word which starts with a letter which is not inverse, but it's inverse inside, but it's not inverse outside. So you use this cocycle up to this multiple. Now you may just consider words which start with a letter which is not inverse. Now you have two cases. Your second letter is not inverse of something, then you multiply it by this cocycle, by the value of this cocycle, and you join these two letters so that you have a word which has length strictly less than the original word. And if the first two letters are this, the letter and the inverse of some letter, Then it's a little bit more complicated. You have inverse of the value of your cocycle and this um, variables here. And you join your letters into one letter so that you have a word which has length strictly less. And this is some induction, yes. So this is a definition by induction on the words, on the length of your word. And that's how you define psi. The idea behind that, I have no time to explain, but the idea behind that, of course, came from the group case. We analyzed what's going on if you apply your action, if you act on a word in a free group. How do you represent the result as a product of those generators of the form xy inverse? And that's how these formulas appear. Okay, well, what's left is to show that equivalent extensions, cohomological cycles, they induce equivalent extensions. Again, this is where induction is used to define those morphisms, so that you have map from this inverse semigroup cohomology, order preserving, to equivalent classes of cross modules. Observe that there is no less than or equal to sign here. So I don't know whether the resulting extension will be admissible or no. And in fact, if T is F inverse monoid, it is. If it's not, I don't know. So restricting our case to F inverse monoids, we have a one-to-one correspondence between these cohomologies and these cross-module extensions. And I think this is the final result. Okay. Thank you. Yes, it exists. It's easier. In fact, it was done for inverse semigroup cohomology. It was done in the same article by Lausch, and it's well, more or less standard. You have short exact sequences of 3 semigroups, which are exact in the same way, in the same sense that I showed here, but only 3 of them. And you have you take a transversal of your epimorphism, you multiply them, appears that guy which depends on two variables, which are elements of your inverse semigroup, and that guy satisfies the 2 cocycle identity, which in our case, no, because in our case we should lift it more and then multiply again, and it gives you a 3 cocycle. But in that situation, much easier. Well, the same idea, but much easier, of course. Yes.
Yeah, so Quillen, in his book on homotopical algebra, gives a definition of homology and cohomology for algebraic theories that involves, so you want, you have your semigroup, right? And then you take a free resolution, and then you essentially home this with the appropriate notion of module, and then you take homology. Now, I wonder, so this is in principle different, but turns out to be equivalent, at least in the classical group, say cohomology or whatever. It turns out to be the same as the usual one. Now, I wonder if one, since in these constructions, free objects appear, whether it might not be perhaps easier to show that you can represent a cross module by a cocycle in a complex that already has to do with taking free resolutions. You know what I mean? I mean, it always depends. I mean, you eventually want to show that equivalence classes or cross modules are the same as the cohomology group. So the cohomology group, you may choose different complexes to define.
Yes. Yeah, different
And perhaps
resolutions.
there are using another choice of the complex, it is easier.
Maybe, yes.
And I was, because of the fact that both in the group case and in the semigroup case, much work is devoted to relating a free object with a cross module. Well, I thought perhaps this approach with free resolutions might be closer in that sense.
Maybe the choice of another resolution would simplify the formulas. Can you give me a reference after the
Quillen's
Uh-huh.
Springer lecture note book called Homotopic Linear Algebra from 1967.
Uh-huh. Okay. Thank you.
All right. Any more questions? If not, let's thank Mykola again.
Thank you.
All right, so now we have, well, I think maybe they're not ready yet, but we should have the last coffee break together with some posters, see if people will put them up, or if not, just a coffee break. And just final thank you for all who made it here, right? It was great to have you here.